Okay, so let's see how to do TensorFlow, the linear regression. I mean, the previous diagram we saw, right? The flow chart which spoke about this journey. So we'll try to implement this, okay, to see how this basically works. First, of course, sorry, 1890. Okay, so first is this. Okay, what we are doing here, we are importing NumPy. Okay, importing TensorFlow. Okay, then from TensorFlow, Python include ops. Okay, what does this contain? This contains all operations, like okay, all operations. And this last thing, you will reset TensorFlow graph. I'll recommend you to do these two lines every time you are executing a new piece of code in your notebook. If you are using the same notebook, if you have some piece of code which needs to be executed, you can use this guy to reset the graph. Otherwise, it will keep on adding data to the same graph. Fine, right?
We can know what are the like OPS, there are different modules, functions.
There are a lot of things. So the only way you will be coming to know about this is from manual, TensorFlow manual.
Okay.
And more by doing it. I mean, as you proceed to the journey, then you start saying, this is one thing, this is one thing.
Okay.
So okay, let's generate some data now. Okay, that's right. Let's generate some data. We'll be doing linear regression using TensorFlow. Okay, that means you have an NP in stage 0 to 10, you have 10,000 data, and this is your y. Understood, right? So what is the slope and what is the intercept if this is the data? 2 is the slope, right? So you want, you're using TensorFlow. This is that you know the relationship between the data. Will not tell. Will pass only x and y. Okay, you know the relationship between x and y. Okay, but okay, so you know the relationship between x and y, but yeah, but you want TensorFlow to predict it for you, the 2 and 5. Let's see how close can it get. Okay, so what is the thing? What is the first thing you do? Remember the diagram. What is the first thing you do? Absolutely, randomly initialize model params. Okay. Okay, so you have A is equal to variable, right? It has to be variable, isn't it? Then TF dot random normal. Okay, we want random distribution, random data with normal. And what is the shape of the data that we want? Right. Shape of the data should be 1 cross 1. A and B, we have to predict a straight line. So what is the shape of the data? Only 1 cross 1, right? Shape. Fine, this is your A. We want to predict AX plus B. This is your B. Right? Okay. Okay. After this, we have to create, what you have to create something in which we can get data from outside, that is training data. What will be that type of variable? Absolutely, placeholder. So when you are passing training data, what all do you pass? You pass X and Y, isn't it? X will be your feature data, Y will be your target data, right? Create placeholders to take data from take training data.
One thing I have a doubt. See, what we have done in this line 2 is we have x is np.linspace 0, 10, and 1000, fine, and y equal to 2x plus 5. But after that, when we have declared a variable, this randomly initiated model parameter, is it the only way to declare, or I can just give some arbitrary value also?
You can give some arbitrary value also. True, you can do that. You can initialize that variable by some arbitrary value also.
Okay, and even I can initialize it with arbitrary value, which is taken from x np.linspace, say x5, and then calculate y and put there.
Actually, the initial value does not matter. So you
Okay,
can take anything. It will initially eventually converge, right? So okay, so now shape of placeholder. Shape of placeholder x means what will be the shape? How shape you will have to pass the entire training data, isn't it? Or a part of training data, isn't it? One will be the number of column, but how many rows? How many? You don't know.
We don't know. Yeah, we have to look at the training data.
Yeah, and it will be flexible, right? You cannot make your model such that it is rigid with input data. It should be able to take 100 data, it should be able to take 1000 data, it should be able to take 10,000 data. Okay, understood. You need flexibility in number of rows. In that case, this is 10,000 data actually. This is 10,000 data.
Generating random numbers, 10,000 random.
No, where? Linspace. No, linspace is not random numbers. It is equally spaced numbers between 0 to 10, not random numbers.
But those are 10 numbers, right?
10,000. 0 to 10. Between 0 to 10, it will generate 10,000 numbers.
Okay. Or it can be 0, 5.1, So here, yeah, so even in spite of whatever the training data you give, it should.
Yes.
So,
okay, so for that you do none. Oh, sorry.
Not enough.
No. You do a none. That means you do not specify any. It doesn't matter actually. You don't need to specify this detail. Okay. Tf dot.
None comma 1 here.
So
one.
None comma 1 because one column you have data. One column data you have, right? Okay, x data. So remember you have to pass rows of one column. Okay, this is your x data, then your y target. Y target, right? You do tf dot placeholder. Right, it will be also same, right?
Yeah, it should also be
none comma 1.
One thing, so this means that x underscore data and y underscore target is like one dimensional.
Two-dimensional data, the number of rows you don't know, number of columns needs to be 1.
Okay.
Number of rows of training data is not something we are aware of. Okay, so now okay, so what is the model matrix model equation? Ax plus b, isn't it? So your model output will be calculate model output. TF, okay, what is more AX plus B, right? TF and, sorry, TF multiply, okay, AX, right? A, what is A is your A, and X is your X data.
X comma X is sorry.
X data. But is it fine if I write A comma X data, or I have to write reverse? What is the dimension of A? 1 cross 1. What is the dimension of X data is equal to this. So I should actually write X data dot A, so that the matrix operation is successful, isn't it? The number of row column here should be equal to number of rows here. Understood what I'm, okay? So, okay, mathematically you will have to write X data comma A. Is it clear why I wrote this? So that it supports, you have to check, because you're doing basic raw maths here. To support matrix multiplication, the number of row columns here should be equal to number of rows. That is why I did this.
If you do the reverse,
It will not work, because it will say dimension mismatch. Matrix, since mat X data and A has 2 underscore matrix operation. Okay, so after this you have to add it with B, isn't it? TF dot add. Fine. This is the model output, isn't it? AX plus B. Okay. After this, you see the model next. So what we have calculated here, we have calculated here till this stage. So what is the next thing that you have to do? You have to calculate loss, isn't it? What is the loss? Actual data minus predicted data, RMSE, root mean squared error. Okay, I think everybody is aware of that. Root mean squared error, square root of sum of a square of difference. Okay. Calculate model loss. Calculate model loss. Now, okay, so loss is equal to TF. So sum of, okay, so you have some operation. So let me do this way. Power you have to calculate, right? Power of TF power comma 2, right? This is square of it, right? And here you have to do model output minus Y target. Is this part clear if I say? What is happening here? It is difference square. Understood? What is your model output? Model output is your output. Y target is your actual target. So you're finding the difference and squaring it up. Then what you have to do? Sum for all data, isn't it? For that you have to call function TF dot reduce sum. Reduce sum means outward. See, if you have an array, if you have a list, what is the content in model output and Y target? It's a list, right? You want sum of these two guys, sum of resultant of these two guys, and eventually you want sum of all those data. So that is why reduce sum, so that so the difference between sum and reduce sum is reduce sum will do the computation as it proceeds.
Okay.
Reduce sum, understood, right? Reduce sum. So you have to do reduce sum here. Reduce sum, okay, of all the data that comes here. Okay, and what is the other thing? You have to remember the maths. It is one. I mean, in case you don't, yeah, square root of, right? And square root's alternative is 1 by 2m. Yes. So in case, I hope it works. Yeah. Okay. So square root's alternative is mathematically 1 by 2m sigma of sum of all those operations. This is what mathematically. 1 by 2m. I think it's not open. Okay, 1 by 2m. You can check out that check out the contents from anywhere. I mean, it is similar to square root of the equivalent is 1 by 2m. Okay, that is what we'll do in this case, 1 by 2m. So divided by linear algebra. You can check. Okay, so I mean, you can check it later, but it is 1 by 2. I mean, divided by 2n. 2 into number of samples you have to do. Okay, so 2 into, okay, what is number of samples? Number of samples is 10,000 here, right? Understood? Okay, but it doesn't look good to hard code it. So what you can do is basically.
Please, go through the last line once again.
So this line, right? This is, I'm calculating the loss.
Okay.
Okay,
so that is output minus the actual.
Yeah, output minus the actual sum square of it and the difference of it and samples, right? So we'll mention and samples.
Why we have divided?
Why have divided? Because the actual error is 1 by actual error rate 1 by 2m. Okay, into sum of square of all the differences. That is the maths of a loss function. Okay. You check out. You can check out this page. Okay, in the regression chapter. Okay, so the actual maths is 1 by 2m. 1 by 2m of the entire thing. Okay, so you can take it offline and check it. Okay, so here and samples I'm putting and samples is equal to 10,000. Understood, right? And samples is equal. This is the loss function here. So I think I've written more or less everything right in this case. Yeah, this is a loss function. Understood what is loss function? This is RMC. Okay. Then you remember how do you find? See, you have the loss function for a particular thing. So what do you do using gradient descent? You will find, what will you do? You'll try to reach to a point at which the coefficients are best. That means the loss function is least, right? Is right. So exactly. So using gradient descent, you'll actually minimize the loss. Okay. And what is one parameter that is required in gradient descent is your learning rate. Okay. So just configure it. Learning rate. Okay, so what is the purpose of gradient descent? Gradient descent is to find the coefficient or at minimized loss. Okay, so we'll use gradient descent to minimize the loss. This loss is this thing, right? We'll use gradient descent to minimize it. See the steps. It is so, it's like storytelling that will happen here. Okay.
So we are actually trying to find the value of A and B at the best.
Absolutely, absolutely. We're trying to find the value of A and B at which the loss is least, and we'll do so using gradient descent.
Okay, right.
Can you check the value before gradient descent?
No, I haven't executed.
That's what we can execute and see.
The loss.
So that we'll see after gradient.
No, we'll see loss also. Okay, when you execute it, it will print loss, it will print all the output. Right. Here you will not see the right information. I mean, you will not see anything at all. Okay.
So the loss function itself takes care of the minimize loss. We have to do the gradient descent.
No, loss function does not minimize loss. Here you're telling how to find loss. Okay. You're not minimizing loss. Okay. So somebody has to call loss function again and again to find the optimum value of it. Minimize loss. Okay. Okay, this is the learning rate. What is learning rate? This learning rate shows step size in loss. Step size in gradient descent. Jump size. Okay, I'll just mention it here in case you want to refer. This is a learning rate. learning rate.
So what actually this learning rate will be doing?
See, gradient descent actually, jumps. I mean, from one point to another point and checks whether this value is good for good. This value is a good loss or not. The jump size is defined by learning rate. Higher the learning rate, it might converge early, but it might skip. It's like jump size. If you configure it too high, it might jump to the optimum value.
Or is it the number of iterations?
No, it is not number of iterations. It is jump size.
Okay.
Okay, that means from one point, from one theta 0 to theta 1, what is the jump it is making to next theta 0, theta 1 to calculate the loss? I mean, in this case, A and B to calculate the loss. If you make a higher learning rate, it might skip the optimum value.
Okay. Okay.
Jump size. Huh?
Point one is jump size.
Jump size in this case. I mean, without a lot of analysis, this was there. Okay, so what is it doing? It is creating a gradient descent for you. Now, what you want to do? You want to use gradient descent to minimize the loss. Train process is equal to gd dot minimize. Understood, right?
So here we use, because there are like other boosting. We have cat boost, XG boost.
Yes. No. That is different. XG boost is different. XG boost is stacking technique in scikit-learn. Here you have boost. What you're saying is gradient boosting. Add boost is here. Right? Okay. Adam optimizer is here. Adam optimizer. We're talking about Adam optimizer. You have, so apart from gradient descent optimizer, there are few types of more optimizers. Okay, which will help to finding the tone. We'll see that. Okay, in optimization, we'll see that. But as we know that linear regression uses gradient descent optimizer, that's why we are using it. In neural networks, you'll see various other optimizers. There are 2, 3 which is more popular.
Because in the R we have this boost, cat boost, like GPM.
Those things are there in scikit-learn here. I mean, I'm not talking about those. It is optimizer actually. So there are 3, 4. So that is a ensemble technique.
Ensemble
technique. Yeah. So I'm not talking. So here also you have optimizers, but those are different. Yeah. Okay. Now what you want to do? This is last chunk of code. Okay. Now A and V are both. So there is something known as batch size. Batch size is equal to 25. That means every time in the entire process, every time you'll among those entire 10,000 data, you'll take 25 data. Okay, compute the loss and do the stuff. So this is a batch size. Every time, what is the number of data that you're using to compute loss and do modifications based on it? 25 data.
Cross validation.
Yes. 25 data, compute loss, change the model parameters. Again 25 data, compute loss. 25 is the size.
So it splits the data into smaller chunks.
It randomly picks it. We'll see this. Will randomly picks 25 data, does the training. Okay, so that is why it gets better accuracy.
Like ensemble technique. Ensemble does the same.
Yeah, in that is how random forest does it from right. Okay. So now what we want to do? We want to try it for 100 times, not more. Okay. We want to try it 100 batches and see how it is converging. Understood, right? 100 batches only.
So every time the batch is whatever value peak in 25, the next batch it won't repeat.
It will take another 25. I mean, it will take randomly 25, not another 25. Randomly.
It's not the same value, it will keep repeating.
Right, I know. Okay. So here, what you do? Okay. It can vary. Some data may repeat random.
Okay.
Randomization is, that's why is a better call. Right? So here, what are you doing? From the entire lot, it is picking up random 25 data. See this random choice. Okay, it is giving you random indexes. Write it here. What is it? Returns random indices from entire lot. Okay. Then okay, understood, right? This is NP random choice. NP is a NumPy utility. What it is doing basically, just taking 25 random. What is the length? Lenx means length of data. That is 10,000. Batch size 25. So it is from 10,000. It returns randomly chosen 25 numbers. 0, 25, 35, 42, 25 numbers. Random index.
So in the next batch, it won't repeat those 25 number.
It won't repeat. It will be some other. I mean, randomly. So may repeat, might not repeat. You cannot assure that.
Like set seed in R, we have
Huh?
set
Syrian, right. Here also it is internally using seed on. Okay. Just I mean, the objective is to get new batch of data. You don't want to train it back with same data, right? You want to train it with new data every time.
But it is always good not to repeat the same data.
Randomization is anyway better. If randomization will make sure that it doesn't use same data again. But of course, I mean, you don't want to bind that way because you might have 50 data only, and you have to train it 25 data. We cannot make sure first. So you'll random sampling. That is the best case. I mean, okay. So you do rand x rand index rand y. X rand y, then it is y, right? Understood, right? Y. Okay, then you do session dot. You have initialized. You call session dot run.
Choice of length.
Train process.
Here given, right? What will be the value?
Well, X is the entire data, 10,000.
10,000 entire network.
Yeah. Okay, training process. Then you will pass. You have certain feed dictionary. Okay. So what is the data you might want to pass here? You have to. I mean, the model it expected X and X data and Y target, right? Okay, you have to pass that. Okay, but remember a few things. You have to when you do this, your training data was continuous, right? One dimensional data, right? You have to convert that into rows of columns. Rows of columns. It was one row of data, isn't it? We have to convert that into rows of columns, basically. Okay.
We'll reshape it.
We'll reshape it, or we can transpose it. Okay, so we'll have to transpose. I mean, just both the data and see how it is happening. Feed. X data. Oh, what was it? Rand X, right? NP dot transpose. I mean, you can of course do the thing anyway. Rand X Y target. NP transpose. Rand underscore Y. Transpose will convert it into rows of columns. Okay. After this, if I percentage, I mean, you don't want to print every time. Okay, you want to print only at interval of 5 times. print loss.
We have an option like stop loss, and it stops where the loss is optimum.
You can write here, right? Based on, you can actually check based on loss. Y target and which line is it complaining? Train process, the first line
You
itself.
have that option lagging, right? Most stop loss.
The same invalid syntax.
So
we have put the
Stops
I think I put more brackets. Next, square bracket, round bracket, into
correct, right? Yeah. This one after that you have to put. No, so this you should change. So the array and the curly braces. Because curly braces is ending, right? So you have to put this.
No, that's right.
Oh, here I haven't closed.
Yeah, here you haven't closed. The
Right.
the transpose.
Right. Here I haven't closed. Now should be fine, right?
Even the next line we did this.
I copied it. So here, yeah, now should be.
Here, this line also will be changed.
Yeah, so here.
You have to close it. Yeah, here you have to know. There are also no space here.
Close it.
Right, you can see the loss getting reduced.
From
Right,
0.4
from 4 to it came 0.208 in just 100 iterations. Okay, again, of course, you intend to print A and B and all that. Okay, we can do that here itself. Okay, so
so this is good, like reducing till to point, and like how do we?
You can give a check here that every time you're calculating, if loss is less than 0.005, stop.
So it is based upon the business specific.
Business specific, right?
So basically, after each iteration, it picks only the optimum values where the error is getting reduced.
Right.
So the error is not random; it's actually decreasing all the way.
All the way, right. So, as you can see, in the 100th iteration, it came to 0.0807. It reached till this point, and it will see, it will always not decrease. It will it will do something. It will see, it will increase, then it will decrease. You see the pattern. It will not ever increase twice. Like once it did something, it increased, then it will again decrease.
Oh, so it's
okay, this is converging.
Like sinusoidal curve.
Right. And I mean, it will see. Okay, it will try this. Oh no, this is not working. Come back again.
What if we have maybe 200 instances like that?
It will be further decreasing actually.
Oh yeah, we can give the number.
Okay, so a simple assignment on top of it. Okay, try to print the values of A and B. Right? I mean, just one line you have to add it over here. Just go through this. Okay, try to print the values of A and B, the coefficient that was finally calculated. Fine, right? Okay, let me save it and upload it.
So this entire line by line can copy it as a whole, like a file kind of.
Just do file download as Python. Download as Python. Okay. We'll stop here. Okay. Next batch is already waiting.
And please upload this video.
Yes, I'll do that.
Yeah, at the channel.
Same place, same channel. I'll upload the video.
Thank you very much.
Thanks.
Code also will upload.
The code also will be uploaded in GitHub.
So tomorrow we do have.
Tomorrow you don't have. Wednesday is not class. Yeah. Wednesday you can always it will be holiday.
So institute will be there.
Institute will be there.
Nobody will be there.